Hello everyone, welcome to my channel Physics with Bhatt. To learn concepts of physics, subscribe this channel and press the bell icon button to get notified for every new video lecture. Good morning dear students. In the last video lecture, we studied about the diffraction at single slit, Fresnel and Fraunhofer diffraction, and under what condition these two types of diffractions occur. In this video lecture, you will come to know about Fraunhofer diffraction in detail, how the fringes are formed. It is just similar to the Young's double slit experiment in interference of light. So, as we know, the Fraunhofer diffraction takes place when the wavefront is plane, that is, both incident wavefront and diffracted wavefront are plane wavefront, and it is possible only if both the source and the screen are at infinite distance from the slit. You can see here, this is the slit and source is away from the slit and the screen is also away from the slit. In above diagram, both source and screen are at infinite distance from the slit, so that the wavefront are plane wavefronts. But this arrangement is quite unsuitable for getting the fringes, so we use some other technique to find plane wavefront in laboratory, and that is we can use in laboratories we can get plane wavefront by using convex lens also. That you will see in the remaining section, that how this convex lens is used to demonstrate the experiment of Fraunhofer diffraction. So just see here the diagram. We are having a point source S here. This is the point source and it is monochromatic source also. We have convex lens L1. This point source is placed at the focus of the convex lens. So these rays which are passing through the focus become parallel to the principal axis and we get the plane wavefront AB. This AB is what? It is plane wavefront, and that plane wavefront we obtained from the source which is lying near with the help of convex lens. Now this wavefront incidents over the slit. So this is the incident wavefront AB. The width of slit is A, and this AN is the diffracted wavefront. The angle of diffraction is shown here. It is theta. We are using another convex lens L2, and the screen is also placed near to lens as well as the plane of the slit. So due to this lens L2, these rays will converge at some point P. That point P is bright or dark, that we will understand in the remaining section of this lesson. That under what condition this point P is bright and under what condition this point P is the position of dark band. You can see incident wavefront is AB, this is incident wavefront, and diffracted wavefront is AN, this is the diffracted wavefront. Angle of diffraction is theta, this is angle of diffraction theta. Due to diffraction, bright and dark bands are seen on the screen. Point P will be bright or dark depends on the path difference Bn. So ultimately everything depends on this Bn. This is the path difference between the waves originated from A and originated from B. So those waves which are originated from B have to travel extra distance, and that extra distance is equal to Bn. So now we will discuss under what condition this point P would be bright or dark. Little more you can understand from this diagram. In triangle ABN, this triangle ABN, if we use T ratio sin theta is perpendicular upon hypotenuse. So perpendicular here is Bn and hypotenuse is AB. So sin theta is equal to Bn upon AB. Now we will talk about positions of darkness, at what point darkness is formed. Let Bn is equal to lambda. Then the wavefront can be assumed to be divided into two equal parts of length A by 2. What we'll do, we will just think of the wavefront has two parts. In place of A, the length of each part is A by 2, such that the part difference between the waves originated from the corresponding points of the two parts is lambda by 2. Just see here, this Bn is equals to lambda, and we have divided this wavefront into two parts. The first part is having points A1, A2, A3, and second part is having points B1, B2, B3. So length of each part would be A by 2, A by 2. This part would be of length A by 2, and this part is also of length A by 2. Then what we are talking about? We are talking about the part difference. The wave which is originated from A and from B, these two waves are having part difference A1, B1. How much it is? Lambda by 2. Why? Because the part difference between A and B is lambda. So half of that is what? Lambda by 2. Therefore, the part difference between A1, B1 is lambda by 2, A2, B2 is also lambda by 2, and A3, B3 is also lambda by 3. We know that part difference and phase difference are related. Phi is equal to 2 pi by lambda into x. So 2 pi by lambda into lambda by 2. So 2 is cancelled, lambda is also cancelled. So phi is equal to pi. I hope it's clear. So phi is equal to pi. This is the phase difference between these two waves originated from the corresponding points. Such waves undergo destructive interference and produce darkness. So हमें जो दो वेव्स मिल रही हैं इन दोनों पार्ट से A1, A2, A3 और B1, B2, B3 है, इनकी जो वेव्स हैं A1 का B1 से, A2 का B2 से और A3 का B3 से, these waves undergo destructive interference and produce darkness. So no light is left. Therefore, this is the position of first darkness. Let this angle is theta 1. Then sin theta 1 is equal to Bn upon AB. So theta 1 is equal sin theta 1 is equal to lambda upon A. Then theta 1 is equal to lambda upon A. So this is the angular position of first darkness on the screen. In the same sequence, if Bn is equal to 2 lambda, then we will divide the wavefront into how many parts? 4 parts, each of length A by 4, such that the part difference between waves originating from the corresponding points of the two adjacent parts. Just see here the division. We have 4 parts, so 1, 2, 3 and 4. So we have to make them in pairs, like if we are having pairing from this side, so A1, A2, A3, B1, B2, B3, these are a pair of 2, and C1, C2, C3, D1, D2, D3, these are pair of remaining 2. So this total is 2 lambda. So if we divide this into 2 parts, then we will have lambda. Again, if we divide the 2 parts into further 2 parts, we will get the part difference of lambda by 2, lambda by 2, and phase difference is again pi. So we will get sin theta 2 is equal to Bn upon AB, that is 2 lambda upon A. So theta 2 is equal to 2 lambda upon A. This is what angular position of the second darkness. So I hope you understood. We are just eliminating the waves originated from the corresponding points of the divided parts of the wavefront. So in general, if you want to write the position of darkness, that comes to theta is equal to n lambda upon A, because for first it was lambda upon A, for second position it was twice lambda upon A. Now for any number of fringe which is corresponding to dark fringe, theta n is equal to n lambda upon A, where n is equal to 1, 2, 3 and so on. So these are the positions of bright darknesses. Now we will talk about the positions of brightness. The bright fringes are formed between two consecutive dark, in similar to the interference of the light. And we have seen that dark fringes are formed when Bn is equal to lambda, Bn is equal to 2 lambda, next is 3 lambda. So in between these 3 values, it is 3 lambda by 2, 5 lambda by 2, 7 lambda by 2 and so on. So if you want to find the positions of bright fringes, then we have to go for the distances in between the above values. So the least possibility here is 3 lambda by 2. So if Bn is equal to 3 lambda by 2, the wavefront can be assumed to be divided into three equal parts of length a by 3 such that the path difference between the waves originated from the corresponding points of the two adjacent parts is lambda by 2 and phase difference is pi. These waves undergo destructive interference and produce darkness, while the waves originated from the third part produce brightness. It is not because of the constructive interference the brightness is produced, just because of the light which is left out in the third part. Just see this in diagram. We have this AB is plane wavefront and this AN is diffracted wavefront. Now we have three parts: A1, A2, A3, B1, B2, B3 and C1, C2, C3. So if I start from the upper end, then the adjacent parts are A1, A2, A3 and B1, B2, B3. So part difference between the waves originated from A1 and B1, A2 and B2 and A3 and C3 would be lambda by 2. If we start from the bottom end, then the two pairs would be like this: B1, B2, B3 and C1, C2, C3. So part difference between B1, C1, B2, C2 and B3, C3 would be lambda by 2. But I have taken here the upper two parts only. I have avoided the lower section. So phase difference is pi. So these waves will undergo destructive interference. So only this part will left out and this part will produce brightness. If this angle is theta 1 dash, then you can see here sin theta 1 dash is equal to Bn upon AB. What is Bn? Bn is perpendicular and AB is hypotenuse. So Bn is equal to 3 lambda by 2 and hypotenuse A. So theta 1 dash is equal to 3 lambda upon 2A. This is the angular position of first brightness. So if we see the formula of first and second dark, this is lying between them. Next we will talk about the second bright. If Bn is equals to 5 lambda by 2, then the wavefront can be assumed to be divided into 5 equal parts of length a by 5. The path difference between the waves from the corresponding points of adjacent parts is lambda by 2 and phase difference is pi. These waves undergo destructive interference and produce darkness, while the waves from the fifth part produce brightness. Just see here what are the 5 parts: A1, A2, B1, B2, C1, C2, D1, D2, E1, E2. These are 5 parts of the wavefront. Out of these 5, if we go for adjacent parts, then from top to bottom these two are adjacent, these two are adjacent, and fifth would be left out. If we start from here, then these are two adjacent parts and this will be left out. So I am taking from top to bottom. Then the part difference between A1 B1, A2 B2, C1 D1 and C2 D2 would be lambda by 2 and phase difference pi. So these waves undergo destructive interference and produce darkness, while the waves left out from the fifth part, this is E1 E2, produce brightness. So this brightness is not because of the constructive interference, it is because of the left out part of the wavefront. If this angle is theta 2 dash, then sin theta 2 dash is equal to Bn upon AB. Bn is 5 lambda by 2. So sin theta 2 dash is equal to 5 lambda upon 2 upon A. That is theta 2 dash is equal to 5 lambda upon 2A. So this is the angular position of second brightness. The first brightness was theta 1 dash is equal to 3 lambda upon 2A. In general, the angular positions of bright fringes are theta dash n is equal to 2n plus 1 lambda upon 2a, where n will start from 1, 2, 3 and so on. If you put n is equal to 1, you will get 2 plus 1, 3 lambda by 2, which is correct. If you place n is equal to 2, you will get 2 into 2 plus 1, 5, 5 lambda by 2, this is also correct. So these are the general positions of brightnesses. If you wish to find linear positions, that is also possible. Linear position of a fringe is always given by the angular position into distance of a screen. So here for dark fringes, yn is equal to theta n into d, and what is the general position of dark fringes? It is n lambda upon a. So yn is equal to n lambda upon a into capital D. So this is what the linear position of dark fringe. Similarly, if you want to find linear position of bright fringes, y dash n is equal to theta dash n into d. Theta dash n is equal to 2 plus 1 lambda upon 2a into d. So you get y dash n is equal to 2n plus 1 lambda d upon 2a. So what is the value of n here? N will start from 1, 2, 3 and so on. If you put n is equal to 1, you will get position of first bright. If you put n is equal to 2, you will get position of second bright and so on. So I hope you understood about the concepts of formation of bright and dark bands on the screen and how to find the positions of bright and dark bands produced in Fraunhofer diffraction of single slit. Thanks for watching this video. We will meet in next video very soon. Till then, keep watching, keep learning.